So in this lesson, I'm going to be talking about another type of equilibria, which is your solubility equilibria. The solubility product constant is KSP, and so we're going to be using the same techniques that we used in the last couple of videos, but now it's with a new concept, which is studying how soluble a solid is in water. Okay? Now there are two terms that we're going to be using, and I want to make sure that we're clear on their meanings. The first is molar solubility, and then KSP. Your molar solubility is the amount of solid that dissolves, and so that's going to be your X. So in previous equilibrium problems where we subtracted by X or added by X, here we call that the molar solubility because that tells you how much of the solid is going to dissolve. Your KSP, your solubility constant, is the equilibrium constant for the equilibrium between your ionic solid and your saturated solution. So that's just your equilibrium constant, while molar solubility is the change in concentration or the change in the amount of solid you have. So the first thing that we need to be able to do is actually write out the equations for the dissociation of an ionic solid. So if I'm given calcium fluoride, it's going to dissociate into its ions. So its ions are going to be calcium ions and 2 fluoride ions. So that's the dissociation of calcium fluoride. What I now can do is calculate the solubility constant for a process like that. So KSP here is going to be equal to, well, the concentration of calcium ions times the concentration of fluoride ions squared, remember products over reactants, and then I might be tempted to put that over calcium, the concentration of calcium fluoride, but keep in mind because this is an ionic compound, it's a solid, and so we're not going to include the solid there, and so for your solubility constant expressions, you only include your products because your reactants, by definition, are going to be solid, so we're going to ignore them. So let's look at an example. So here it first asks me to write a balanced equation for calcium hydroxide dissolving in water. So I start off with calcium hydroxide, and it's going to dissociate into its 2 ions. It's going to dissociate into calcium ions and 2 hydroxide ions. There you go. So now, if I look at the next question, it says the solubility of calcium hydroxide is 0.012. Keep in mind that the molar solubility simply means your X. So the concentration of calcium ions and hydroxide ions is going to change. The X for this is going to be 0.012. So I'm actually going to rewrite my dissociation right there. I'm going to create an ice chart because this is an equilibrium problem. Keep in mind, because calcium hydroxide is a solid, I'm going to ignore that completely and just look at calcium and hydroxide ions. So I don't start off with any calcium or hydroxide. I know that I need to add X and add 2X for the hydroxide. However, keep in mind, I've already been told what my X is. My X is 0.012. And so what I can do is say, all right, at equilibrium, my concentration of calcium ions is 0.012. While my concentration of hydroxide ions is 0.012 times 2, which gives me 0.024. So those are my 2 answers for right there. Really not that bad. The last thing I need to do is to write the equilibrium constant expression and calculate my KSP. Well, again, KSP equals simply my products, so calcium ions times hydroxide ions squared, over my reactants, but again, remember, because it's a solid, I ignore it. So all I have to do now is plug in the values I got for the equilibrium concentrations of calcium and hydroxide ions, and I'll get my equilibrium constant, just like what we were doing before in the previous lessons. So I'm going to take 0.012, multiply that by 0.024. Remember, I need to square that value because there's a coefficient of 2 for hydroxide. And what I end up getting for my KSP is 6.9 times 10 to the negative 6, and that's it. What we're going to look at in this section, there are 3 different factors that can affect the solubility of an ionic compound, basically its ability to dissociate into its ions. And the first one is one we've actually already looked at, the common ion effect. And so just as a review, the common ion effect tells us that the solubility of a slightly soluble salt is going to decrease if there is a second solute present that has a common ion. And so we actually already looked at this in this unit, but let's look at an example to make sure we're clear. So if I give you lead 2 chloride dissociating into its 2 ions, lead ion and the chloride ions,
if I were to add HCl to the system, what's actually being added that I care about is that chloride ion, because notice I have chloride in my products for this. And so chloride's being added, and so that's going to cause a shift. And remember, this goes back to the previous unit with equilibrium. It's going to cause a shift to the left because I've increased my concentration of chloride ions. So the shift is going to be to the left. And so if you think about the solubility of PbCl2, if you've shifted to the left, that means lead chloride is going to be less soluble, so the solubility is going to decrease. If it had shifted to the right, then the solubility would have increased. So that's one factor that affects solubility. The second factor is pH. Okay? So if we look at, for example, magnesium hydroxide dissociating into its ions, if I were to go ahead and I were to add sodium hydroxide, in your mind you should be thinking, well, hydroxide is the ion that, this is basically a common ion effect problem. Hydroxide is what's being added, and so that's going to cause the hydroxide ions in my products to increase, which means I'm going to shift to the left. All right? If I shift to the left, that means that the solubility of magnesium hydroxide is going to decrease. This seems like I just repeated myself from the previous section. However, what I'm talking about is pH. So in this case, I increased the pH by adding sodium hydroxide, which then caused a shift to the left, which caused my solubility to decrease. Sodium hydroxide was added, so since that's a common ion, that means that the salt's going to be less soluble. Well, what if I don't add a common ion? What if instead I add hydrochloric acid, for example? Well, that isn't an ion in that dissociation reaction. However, what you should notice is that I'm adding H+. Well, H+ is going to react with hydroxide, which we learned in this unit, and it's going to form water, which means the concentration of hydroxide ions is going to decrease, which means you're going to have a shift to the right. And if you shift to the right, that means your solubility is going to increase. So the second rule here is if you add an ion that's going to remove one of the ions in solution, then the solubility is going to increase. So the only new term here, this is Le Chatelier's principle. The only new concept is this concept of solubility. So if it's shifting to the right, that means that the ionic compound is going to be more soluble. If it shifts to the left, it is less soluble.